This is being recorded at the University of Bern on the 9th of July of this year. Ladies and gentlemen, I want to start by thanking the prize committee for selecting me for this ICL-Prize. I do appreciate it. I feel honored. And I want to apologize to all of you for not being able to be present at this meeting personally. My mobility is severely impaired at the moment, and Brazil is outside my radius. I'll try to keep this short and not bore you with too much old science. Rather, I'd like to share with you a few impressions, a few reflections on how our science has developed in the last 40 years. And this very short outline already indicates, in the very early days of my research activity, luminescence spectroscopy was mainly used as a tool to study fundamental physics, energetics, dynamics, energy transfer, relaxation, you name it. And then gradually the focus moved towards a more materials-oriented focus with light emission as the main property of interest. I'll show you one example from the early days and two examples from the later days. I want to start with this gentleman, Jim Ferguson, Australian National University in 1972. When I joined his group as a postdoc, he was my teacher. He was an outstanding experimentalist, had been at the Bell Labs for many years, and he taught me everything about optical spectroscopy, absorption, luminescence, low temperature, high resolution, crystals, polarized, and so on. Here you see him with a Carry 17 absorption spectrometer. Please notice the very simple device used for cooling the sample, just a flow tube sticking in the container. And you also notice that the spectra were recorded on paper in those days. That was way before the digital age. Another noteworthy observation is Jim's attire. It was not at all unusual in those days for professors to wear a tie while doing experiments. Quite in contrast to these characters here. On the right, Terry Wood, a PhD student in Jim's group. Slightly out of focus, you see some important tools. On the uppermost shelf, a tennis racket, an indispensable tool in Australia. And then the stacks of punch cards, our computer input, and the big stacks of white paper, our computer output. And now I'm coming to the first scientific example, Ruby. There are hundreds, maybe thousands of papers on the Ruby R lines, the red lines around 700 nanometers. And here you see absorption spectra of rubies of different chromium concentration. The upper left panel shows the spectrum of a chromium single center in a slightly distorted octahedral coordination. With increasing chromium concentration, side bands are coming up on the low energy side, and these bands are due to chromium dimers and trimers. But the problem with the corundum structure is that there are many different types of dimers, and the spectra of these species are superimposed. It's very difficult to take them apart. So I suggested to Jim that I would make a material containing only one type of dimer and no single ions. He had never heard of this, but he was interested. So, being a trained coordination chemist, I put on the lab coat and made this dinuclear chromium complex. A hydroxo bridge between the chromium ions, ammonia ligands completing the coordination. And this hydroxo bridge causes the chromiums to interact antiferromagnetically because the d orbitals of chromium overlap with the s and p orbitals on the oxygen. This is called exchange interaction, can be represented by a Heisenberg Hamiltonian, and this interaction is responsible for phenomena such as ferromagnetism or antiferromagnetism in oxides and halides. And that's why in those days physicists and magnetochemists were very interested in studying these simple dimeric units to get insight into the nature of these couplings. Now the exchange splits all the energy levels of the single ion chromium, and our aim was to directly measure these splittings by spectroscopy. And it worked. Here on the right you see, again in the region of R lines, 4 distinct electronic lines, and they can be readily assigned, as showed on the left, to transitions from the emitting state to the 4 levels of the ground state. And from these splittings, both in the ground state and the excited state, we gained considerable insight into the nature of the coupling. Now, this work had essentially no resonance in luminescence spectroscopy circles. And I guess most of you, maybe all of you, have never heard of it. But it was noticed by magnetochemists and physicists, an area of research which later became known as molecular magnetism. This already brings me to the second part. I'm jumping a couple of decades. I'm jumping into our work on upconversion. I guess most of you are familiar with the principle. 2 or more low energy excitations produce a higher energy emission. And you also know that the most suitable ions for upconversion are the lanthanides. They're standing out here, and especially the highlighted ones are important upconversion ions. Ytterbium often serves as a sensitizer, an upconversion sensitizer, because it has a relatively strong absorption around 1 micron. We also found upconversion in some transition metal ions, nickel 2+, titanium 2+, molybdenum 3+, rhenium and osmium 4+ in suitable lattices. Please notice the green and the blue materials on the upper left. Sodium yttrium fluoride doped with ytterbium erbium or ytterbium thulium. These materials had been known since the early upconversion work in the 1960s, and they were known to be efficient upconverters, but nobody knew why. So we thought we could use our chemical expertise again, extend the range of host lattices beyond the fluorides, the chlorides, bromides, perhaps iodides, and with the hope to induce new upconversion processes, new upconversion colors. And I'm showing you one example. Erbium is the upconversion ion par excellence because of its very favorable energy level structure. It can be excited in many different ways by upconversion. Here we see an excitation around 1 micron, bringing it up to quartet F 7/2. We put it in chloride and bromide lattices, here 2 isostructural lattices. The upper trace is a chloride, the lower a bromide, and the upper one is an almost pure green luminescence, whereas the bromide is an almost pure blue luminescence. So we had immediately an effect. And the nice thing with this one here is that we can explain the different color very easily. And I'm going through with this very briefly. In a heavy halide, iodide, bromide, the phonon energies are small. After upconversion excitation, we get immediate blue emission. In an oxide or fluoride, however, phonon energies are bigger. Multiphonon relaxation is more efficient, and the system relaxes to quartet S 3/2 before it luminesces green. Chlorides, finally, are somewhere in between. Some are blue, some are green. The example we've seen just before was a green one. So, scientifically, this was very neat. We are able to rationally tune the emission color by chemical variation. However, as an attempt to make a useful material, it was a failure. We tried very hard in the early 1990s to make a blue laser based on this principle, but we had to realize that these materials were simply too hygroscopic for such an application. So we grudgingly returned to the mainstream, so to speak, to the fluorides. We played around sodium yttrium fluoride, sodium gadolinium fluoride, sodium lanthanum fluoride, doped with all kinds of lanthanides, combinations of lanthanides, lanthanide transition metals. We did a lot of rather sophisticated spectroscopy, time-resolved, 1-color, 2-color excitation as a function of temperature. And we did learn a few things about mechanisms. We also came up with a tentative explanation why these lattices are particularly suited for upconversion. I'm going to skip all this and jump directly to my last scientific slide. In 2004, we published this figure. It was the first demonstration of upconversion luminescence in a completely transparent solution based on nanoparticles. I guess many of you have seen pictures like this, and I think it's fair to say that our work was the starting point for quite an astounding scientific development. We were out of it, unfortunately, because I was retiring pretty soon after this, but many groups took it up. Already a couple of years after this, many groups had realized much better particles than ours had been. Monophase, a narrow size distribution, covered with a surface that made them water dispersible. They could be substituted on the surface. And I can only look back, and that's what I did a couple of months ago, Web of Science. Here are plotted the number of citations per year if you put in upconversion. And I guess those of you in the background cannot see it, but we are up to more than 30,000 citations per year. 30,000 citations. How can you keep abreast of developments in a field where there are 30,000 citations? I don't know. But you see, the main rise happened in the last 10 or 15 years. And I can tell you that most of these citations are on nanoparticles, on upconverting nanoparticles. And there are certainly several reasons for this surge. I guess one of the reasons is the relative ease to produce such materials. You can do it in a normal chemistry lab. You don't need high temperature equipment, protecting gases, things like that that you need to make crystalline material. But I guess the main reason is that these materials have considerable potential for applications, mainly in the fields of biology and medicine. And that brings me to the acknowledgements. I've had the privilege to work with many outstanding scientists in the course of my active research career. I won't name them all, but I want to thank them all. The University of Bern and the Swiss National Science Foundation have been generous in supporting our research. And finally, I want to mention one more person, Rino Di Bartolo. He never received the ICL-Prize, but he should have. Not so much for his scientific achievements, but for his great efforts to build a community and keep a community together over years, over decades. Starting in 1974, he has organized schools, workshops on luminescence and related topics in Erice on a very regular basis until this year. In my view, his contributions to our field, to our community, to our science are invaluable. Here you see him in 1974 at the first school on atomic and molecular spectroscopy in Erice, in the San Giovanni monastery. I had the privilege and the pleasure to attend this meeting, and it was very memorable. Many important people in luminescence attended, but most memorable for me is the social part. It was the coming home, so to speak, of Rino. He had grown up in Trapani, close to Erice, become a professor in Boston, and this was the first time that he came back professionally. His parents were still alive, his relatives, friends in Trapani. They came up every evening. We had party, we had music, singing, dancing. And here, 40 years later, Rino still looking strong, still teaching special relativity at Boston College. I wish him well. And with this, ladies and gentlemen, I close this presentation and say goodbye.